LM inference traffic is rarely smooth. A single burst can create queues, latency cliffs, or wasted GPU spend. In this lesson, we'll turn unpredictable demand into token-aware capacity plans that scale reliably without surprising your users or your cloud bill. So far, we've seen why naive LLM apps fail in production: runaway token cost, latency spikes, cascading errors, GPU memory issues, and drift. Then we rebuilt the foundation with controlled inference, open-weight models, vLLM, optimization, and routed fallbacks. Now that the platform exists, the next challenge is capacity: how much to run, when to scale, and how to stay efficient. Autoscaling a web API is often simple. Watch CPU or request rate, then add replicas. LM inference is different. One request may be tiny, while another consumes huge compute and memory, because prompts, outputs, model size, and decoding behavior vary. GPUs also depend on batching and KV cache. Scale too late and latency jumps. Scale too early and expensive GPUs sit idle. The goal is to balance cost, latency, and availability. In LLM serving, a request is not a reliable unit of work. 10 short questions may be easy, while one long document summary can keep the GPU busy for seconds. Capacity planning should start with tokens per second. Input tokens drive prefill work, and output tokens drive decode work, so track them separately when possible. Request rate still matters because it describes traffic volume and concurrency. But token rate shows compute pressure, and it is usually the better signal for sizing GPUs and setting limits. LLM serving has two distinct pressure points. Prefill happens when the model reads the prompt. Long prompts can burn a lot of compute up front, so latency may spike before the first token appears. Decode is different. The model generates one token at a time, and each active request continues occupying GPU capacity. Long contexts also expand the KV cache, reducing how many requests fit in a batch. Good autoscaling watches both pending input tokens and active output tokens because they reveal different bottlenecks. Baseline capacity starts with demand, but plan for peak tokens per second, not average requests. Profile real prompts and completions. Then benchmark the exact serving setup: model version, GPU type, quantization, context length, and batching. That gives you sustainable tokens per second per GPU. From there, required GPUs is roughly peak token demand divided by sustainable GPU throughput multiplied by a safety factor. That buffer covers burstiness, retries, failover, and priority traffic. Finally, validate the estimate with load tests that match production distributions, not synthetic happy paths. Effective LLM autoscaling depends on a set of signals, not one magic number. Queue depth shows that requests are backing up, while pending tokens shows how large that backlog really is. GPU utilization indicates compute saturation, and memory or KV cache pressure shows when batching or context length is becoming the constraint. Latency closes the loop. P95 and P99 time to first token plus end-to-end latency reveal what users actually feel. Scale when these signals agree, and avoid reacting to noisy spikes. Queue-based scaling focuses on work waiting to be served, not just CPU or GPU utilization. For LLMs, pending token backlog is often more useful than request count, because one request can represent a few tokens or a huge generation. When estimated queue weight crosses a threshold, request more replicas before users hit the latency cliff. Keep thresholds separate. Interactive traffic should scale sooner than batch or background work. Smooth the signal and use cooldown periods so the system responds to real pressure instead of bouncing on brief spikes. GPU metrics are valuable, but only when you read them alongside latency and queue behavior. 90% compute can be healthy if requests are flowing, batches are efficient, and tail latency stays flat. Memory pressure is different. A full KV cache, oversized batches, or long contexts can push the system toward or forced eviction. Also, watch the inverse pattern. Low GPU utilization with high latency often points to scheduling overhead, fragmentation, or an upstream bottleneck. Correlate DCGM or NVIDIA Semi with vLLM, Gateway, Prometheus, and OpenTelemetry metrics before deciding what to tune. Latency is the symptom users actually feel, so it belongs in the autoscaling loop. Measure time to first token separately from total response time, because a model can start slowly even if the full answer eventually completes. Focus on P95 and P99, not averages, since tail latency is where users see stalls and timeouts. The caution is that latency often rises after the system is already overloaded. Pair it with earlier signals like queue depth and pending tokens, so scaling starts before experience degrades. Cold start time is the hidden tax in LLM autoscaling. A scale trigger does not mean capacity is ready. The system still has to schedule a container, pull or mount the image, load model weights, reserve GPU memory, initialize the runtime, warm kernels, pass health checks, and join the serving pool. For large models, that sequence can take minutes. Sometimes the traffic spike is over before the new replica is useful. Scaling policy must predict demand early, keep warm capacity, or use staged loading instead of reacting only to the current queue. Warm capacity addresses that cold start problem directly. A warm pool keeps a small set of replicas loaded and ready, even when demand is low. Predictive scaling goes further. If a product launch, batch window, or daily peak is coming, you add capacity before users arrive. In practice, many teams use a hybrid model. Pay for baseline warm capacity, then let autoscaling handle surprises. The right balance depends on GPU cost, traffic predictability, SLA strictness, and model load time. During demand spikes, the goal is not to serve every request equally. It is to protect the work that matters most. Priority traffic, such as production users, safety-critical actions, or control plane calls, gets reserved GPU capacity. Standard and background traffic can queue, slow down, or be rejected when limits are reached. Admission control enforces that boundary, so lower priority requests cannot consume every slot. This turns overload into a planned trade-off. Critical workflows stay responsive, while best effort workloads experience controlled degradation instead of causing a platform-wide outage. The worst response to a spike is to accept everything and hope the queue clears. That creates runaway latency and can take the whole system down. Make overload a controlled decision instead. First, protect high-value or time-critical traffic. Then reduce cost where possible. Shorten outputs, route to a smaller model, serve cached results, or move work to async processing. If capacity is still exhausted, shed low-priority requests deliberately. Use clear semantics like 429 and retry after, so clients know what to do. Most importantly, make these policies explicit, measured, and tied to business priorities. To wrap up, LLM serving capacity is not just about request counts. Track tokens, queues, GPU pressure, memory, and tail latency together. Plan for slow model startup with warm pools or prediction. Under overload, protect the most important traffic through buffers, priorities, shedding, and graceful degradation. Next, we'll reduce and contain load with caching, deduplication, circuit breakers, and fallbacks.